welcome everyone. So it's a great pleasure to have Juven Wang from Harvard giving us a seminar today. So Juven, graduated from MIT and subsequently moved to IAS and now at Harvard. And Juven has done many great things, and he's one of those people who doesn't fit into a single box. Sometimes it's hard for me to define whether Juven is a condensed matter theorist or high energy theorist or mathematical physicist. He's probably everything. And he's going to tell us some recent works that he's been doing that kind of fits this theme of unification. So Juven, it's all yours.
Thank you very much. Thank you, Tom. It's my great honor to speak at this highly praised perimeter seminar, and also I was there many years before, and it was really a great time. I'm sure that this place has evolved into even more. This world-renowned research institute. So thank you, Tom, for the opportunity to speak. I should post again. The slide are available, so please feel free to download it. It's on the Dropbox link in case. I think it should work. But if it doesn't work, let me know. Please feel free to interrupt me if you have any question. And I will apologize if I go slightly over time, but I'll try to take control. So the title is Ultra Unification. This ultra will be explained later by along the line of people explore about this ultra quantum matter. Many of you might be familiar for condensed matter people, but I will just give some kind of explanation later why this is a name. And the kind of thing we have today is about quantum criticality. For quantum, I really mean a zero temperature. So extremely quantum effects is more important. It's not just a thermal phase transition for thermal effects. It's really a zero temperature quantum effect. And criticality here means some gaplessness evolve. And for people who study scale invariant, conformal invariant CFT, these are the zero temperature type of a phenomena, phase transition. And the deformation is what I'm going to introduce to tune in some quantum field theory, particularly the standard model. This is based on work done with Zheyan Wang and Yi-Zhuang. I would like to acknowledge their support is enormous, and their collaboration are really wonderful together. Mainly based on the paper this year, especially the one in blues. And I should remind you, if you see the newest version, either post on arXiv or the Juno version, please look into the newest one, because when I try to learn from feedbacks from other field, I sometimes will change or improve my description, so maybe more people can access or understand what I'm trying to do. And for example, like the first paper, actually the arXiv E3 are recently posted, just try to make many more math and physics statement more precise. Okay. All right, so one open question in high energy physics is how the strong EM and the weak forces in the standard model SM are unified at high energy. So those are the forces confirmed by experiments, and we already have a framework. Conventional view is that this SM is a 4D Lorentz invariant renormalizable quantum EFT, effective field theory, and quantum field theory. And smaller gauge group might merge into a larger gauge group. And the Grand Unified theory, some version of it, called GUTS for short, will be play some role. People hypothesize that supersymmetry might join in, and even more high energy might go to string MF theory. So these are the energy scale we are tuning at an energy scale higher and higher. So we probe shorter and shorter distance. While the horizontal axis here draw for not particular meaning, we just nothing. So really people looking at high energy and short distance. Okay. So the second viewpoint, which I will go into today, is that the proposal or kind of a thinking we are heading into is that SM is a 4D EFT, and only one possible phase among many phases of the vacuum we can leave for our universe. And we will strictly focus on mostly zero temperature, T equals 0 quantum theory. And the neighbor might have a lot of God phases, Grand Unified theory phases. And we would like to understand, for example, whether there are some parent effective field theory, EFT, control the tuning from SM to neighbor God phases. So SM may emerge, we will show in some example, near the quantum criticality, some near the phase transition or near the gapless region. So these are the general picture. So in this scenario, not only we can tune the energy scale as we used to pull the shorter distance and collide with higher energy. But we are thinking about whether we can also tune other parameters. There could be many parameters. So these are plural, many possible parameters. And I will introduce some of them. And one of them will be a gut Higgs potential. So which means how do we condense the Higgs field, breaking down the Gauss gauge group. Okay. For example, there could be some 5 square 5 fold terms, and we can tune the 5 square 5 fold term coefficients. So these are the things we will tune in. And you will see that I'm summarizing the result now, but just you will see that the SM standard model phases, if they are somewhere like this region, actually it can occur near a critical region that I draw in the shady area. So there may be additional new beyond standard model BSM degree of freedom come naturally if you're thinking about this picture. So let me just say related ideas. These are not totally bizarre because this idea has been known for many people. Like recently, Seiberg summarized his proposal on deformation class of quantum field theory in Spring 2019 meeting. And McNamara and Fafa, they actually proposed something called cobordism class for quantum gravity theory, putting a theory involving gravity with some internal symmetry gravitational probe and try to ask what are the cobordism group. And cobordism group are a way to classify a manifolds with certain structure. And then they say that if the theory on one side has a non-trivial cobordism class, which means non-trivialness, then the domain wall on the other side must combine together to cancel. And there's some constraint. So the whole thing there is more like a trivial cobordism class corresponding to something like anomaly cancellation, that type of statement. But right now, I'm just giving you some related statement and knowing that we are actually along the direction also other people are heading. And for some people might be familiar with earlier, like there's some study people try to understand regularizing chiral fermion on lattice. Certainly this is an old problem, but there's a this new development or new kind of new perspective trying to using this classification of topological phase to understand this. And in that perspective, actually, these are along the line of this cobordism class statement. There, the statement is, let me just say briefly, is that if I have a theory of a chiral fermion, just like our standard model have a chiral fermion, then it can be possibly thinking about as a domain walls fermion theory between phase A and B. And if the B on the other side has also the A phases, then there will be a fermion doubling with the opposite chirality. Okay, but the question there is that suppose I put the chiral fermion on some quantum system. Usually when you try to put it on some system like a domain wall fermion, there will be a doubling if you put it on some finite system. So the question is that, for example, are there a way we don't really have this doubling non-chiral theory, but remove the chiral doubler? And if you follow what I just mentioned about this statement about deformation of quantum field theory, then let me say that it says that within the same symmetry, global symmetry G, and within the symmetries anomaly, anomaly, the different type of a quantum field theory with the same symmetry and anomaly can indeed be deformed to each other via 18 degree freedom at a short distance, or pulling from high energy 18 degree freedom, and such that they still preserve the same data of G and the topo anomaly. So these are the kind of thinking along the understanding of this deformation class quantum field theory. If this is clear, then the mirror doubling side actually can also be gapped. At least exists also a gap phase, gap in the mirror fermion. And that's a kind of consistent statement about this, the idea for this deformation class. And okay, so let me just pause for a second, just make sure whether anyone has a question about what I say so far. So this is a perspective we will use today. We will not explore just high energy, that's also possible, but we will also explore tuning the quantum vacuum by doing like phase transitions at zero temperature. And this parameter space can be labeled, for example, by the symmetry G and the whole anomaly, and that control the deformation class. And on the other hand, given this symmetry G and Tohu anomaly, we may be able to aid potential or other things to do this deformation. Okay. So there are different data to do this control. One is this G and Tohu anomaly. The other is some additional field theory parameters that try to move the left. And it will become clear when the talks go on. So let me also mention a few things about the standard model just for a review. The standard model has, which we will count now, is like 15, possibly +1 or possibly not, biofermion or biospinner. And they are coupled to Yang-Mills gauge theory with this D algebra, SU3, SU2, U1. They are in certain representation, which is shown in this cartoon. And each disk is a biospinner, 2 component, left-handed, or in these figures, left-handed, in spin 3,1. And you will see, for example, this quarks U and D in the left-handed are SU3 triplet, red, green, blue, and also SU2 doublet. And the right-hand quarks has this singly on the SU2, and there's a triplet again on the SU3. And there's also left-hand sectors, the neutrino and electrons for the first generation. And then there's also doublet and singlet. And notice that there's a question mark here. This one actually hasn't been confirmed solidly in experiments, even though in theory, people hypothesize or study it. So I think it should be clear for theorists what is the thing confirmed by experiments and what the thing is not. So this is thing will play an important role actually in the part 2 of my talk. But right now I just want to kind of highlight this. This will be important. Written out the representation in a precise form, this will be the so-called stereo neutrino or right-hand neutrino, even though we flip all to the left-handed, but this one will be there or will be not there in some of the scenario I will discuss today. We will see whether they are there or not affects which deformation class we live in. We can move the vacuum in different way. And also remind you the standard model gauge group that globally they could have a different mass ZQ, all compatible with this representation. It's not determined yet. There's a mass ZQ of 1, 2, 3, 6, depends on the center of this gauge group. So the open issue we will also touch, actually more in the later part of my talk, but I just want to kind of give you some preparation that we are hitting there. Neutrino, right-handed, whether they exist or not, and if they are, how many there are actually. There are 3 generations of quarks and leptons. Are they all there? And we can also ask how the left-hand neutrino get mass. Is that just through the conventional bilinear Dirac-Morana masses? And today we'll go to another resolution, possibly later on this we'll call Ultra Unification plus some additional things. These are other ways to get masses. And these are a theory that contain standard model and also Grand Unification. This model also provides other way to get masses. We can replace actually some of this biospinner, right? There's a 16 biospinner, the right-hand neutrino, by 4D new sector TQFT or CFT, or 5D invertible TQFT, so topological field theory or conformal field theory. But the way we replace this is carry the same anomaly index, which I will show. So the kind of observation is actually based on development on discrete symmetry, especially baryon minus lepton, and global nonperturbative anomalies and cobordism. So any question about this slide, please feel free.
I have a question.
Yeah, please.
So I don't know the standard model very well, but in the standard model, is there a particle that is a doublet on the SU2, but charge neutral on the U1?
So we can look at this. Which U1? You are saying the U1 EM or U1 hypercharge? Yeah, I should mention this Y is hypercharge, and X is something related to B minus L, which I will introduce. These are some X is some linear combination B minus L and hypercharge. So you ask the doublet whether there's any trivial on the U1 EM or U1 hypercharge. I think the answer is no if you just look at this U1 hypercharge.
So the answer is no.
No.
Okay.
Yeah.
So if the answer is yes, if the answer was yes, then you know that the Q case doesn't.
Yeah. So I think maybe you should report your name in case Liu Jun, right? So Liu Jun, I think he's trying to say whether certain particle, if they are there, they can indeed rule out some gauge group, yes. But in this case, we cannot rule anything because given all this representation, they are all compatible with any mass EQ. Okay. Any other question? Yeah. Okay, so these are basic standard things. Also, the slides are available. I would really want to have people follow, so you can feel free to download the slide from the chat. If you have trouble to access, let me know. So what we will go in the very end of my talk, this Ultra Unification contains standard model, or the BSM standard model star, the BSM section we call standard model star, as again the 4D EFT live on the boundary of some 5D, possibly gapped or even gapless topological theory. And they are topological force and matter evolved in the fundamental physics in the same way, just like SM, gauge group. And they are a possibility constrained by cobordism and anomaly consistent. And I think that's the whole thing about this proposal. It's not that just randomly adding new sector without any reason. There's a reason for just like a anomaly cancellation reason. And I certainly need to modify more, but just let you know it's not randomly add something. So many partial faces are allowed. And the neighbor faces in this scenario contain either 15, that I count for you, there's 15 without right-hand neutrino, sorry. We exclude this one, the 15 or the 16. And this so-called this UU is actually the way you can move between those vacuum and control the phase transition. You can think about parent EFT. Okay, so again, the UU, this Ultra Unification will just replace some stereo neutrino with new exotic gap or gapless sectors in 4D or in 5D, and such that the whole thing cancel certain anomaly cancellation, or just cancel the global anomaly and satisfy by some cobordism constraints. In certain cases, I think even gravity, more topological kind of gravity can come in. And I won't be able to discuss today because these are more subtle and I'm still trying to work on it. And we don't have Einstein gravity, by the way, at this moment. So these are not right the unification as ambitious as string theorists. It's really just some kind of additional degree of freedom. We are able to move between GOT and adding TQFT, CFT sector. If you are pheno-based people, you might think we actually have a room to interpret some mysterious data that is beyond standard model, BSM. So these are kind of the thing I'm thinking. So I'm not going to say anything above certain scale, possibly string theory or other things. It's really just below certain energy scale. And Einstein gravity hasn't played a role here, except that we only consider background gravity probe put on theory on curved manifold, and there's a gravitational anomaly constraint. So any question about this slide? No. So let me, just in case, I don't know how much. Yeah.
So I mean,
yes.
I don't understand. You include gravitational anomaly, but there's
yes.
What is gravitational anomaly here?
Yes, I'll go there. Okay. You can think gravity as some background probe. So you have a curved space-time. You just want to put a theory, for example, on SO spatial orthogonal group, structure manifold, spin manifold, and you can think these are probe field. If it's dynamical, then actually, whether it's dynamical or not, actually, in the end, I do want to demand gravitational anomaly cancellations. So you can think there is some dynamical gravity effects, except that I don't really consider the manifold, the geometry, matrix, that type of things. I just consider these are largely kind of, you can maybe say no back reaction. It's not really go to quantum gravity. There's no like a matter field distort the space-time, that type of effects. It's just like putting on curved manifold.
Right, but I guess I'm just wondering why do we need a gravitational anomaly cancellation if there is no?
Okay, very good, very good. So that will come into an important point much sooner. So there's one thing: if gravity is a probe, then this will be regarded as more like a tuple anomaly of the type of the space-time internal symmetry, and space-time diffeomorphism. That anomaly can be an indicator of the theory. Does not need to be cancelled. But then later on, I'll give you some motivation. In certain case, gravitational anomaly better to be cancelled. Yeah, okay. I'll state this. Yeah, so please ask again. This is a very good question. Thank you. So let me just, since you mentioned anomaly, let's just discuss a few cases. I think these are standards, so be very quick. We are really consider invertible one, and they are local perturbative anomaly classified Z, or non-perturbative one, a Zheyan class. And the Z class, for example, the ABG anomaly, usually in 3+1D, there's something like QL, if it's a U1, QL cube, QR cube. So these are like some integer numbers. So these are the number for discuss this anomaly class, Z class. But the Z2, Zn class, for example, Z2 familiar SU2 Witten anomaly is a Z2 class. So these two such an index can cancel to be nothing. So these are distinction from this class of anomaly. And the D-dimensional Tahu anomaly is actually an abstraction to gauge a global symmetry G, and which we put on G bundle with some G connection. It does not mean the theory is ill-defined for quantum field theory with G Tahu anomaly. It's just a signature for the theory has a difficulty to gauge a global symmetry. So as what you are saying earlier, it's a signature for the theory. It's not sickness of the theory. But this lead to ill-defined G gauge theory. And we still can use as a background probe field to probe that and constrain the quantum dynamics. And we can detect that by doing couple to some symmetry background field and do a symmetry twist. And then we can read some U1 invertible phases, and hence the name invertible. And later on, we'll specify this G not just for the internal like gauge group or global symmetry, internal symmetry or gauge group, but also the space-time, and such that they will be able to share some finite group. Although this common modular theorem said we don't really have a non-trivialness between the more like a Lie algebra between the space-time or internal, but we do have a finite sectors that's possible, like Fermat parity. So in my talk later on, you will see this space-time internal, they could share a Fermat parity, like a graded spin group rotational SO, and the internal symmetry of some internal gauge group can share the Fermat parity Z2F. So this will be the G symmetry will be considered. So this anomaly, Tahu anomaly, contain probe of the gauge internal symmetry probe, and as well as a space-time diffeomorphism probe. And for condensed matter people in this audience, we know the internal G symmetry cannot be put on local onsite in the deep lattice or cutoff scale or UV. So these are non-anomalous non-onsite. It's still difficult or not possible to gauge such a non-onsite symmetry, unless you handle this in some additional way, like putting on higher dimension, one higher dimension is boundary. And for math people, which we will use the data, this invertible TQFT in D+1 dimension was specified by cobordism invariant and written in this data. So there's anomaly info between D and D+1, D+1 dimension, one high dimensional invertible phases specified by this U1 phase. And there are some dynamical phase if such an anomaly is there. We cannot have a G symmetric trivial gap phase, but there's some like G breaking or additional gapless degree of freedom to saturate this G Tahu anomaly. Okay, and I just want to mention that people will be familiar now. If I just mentioned earlier, say this Tahu anomaly is this type, like we use global symmetry probe, but this does not need to be canceled. Well, the textbook check the dynamic gauge anomaly is this type, this gauge probe, so this need to be canceled. But we will need to switch between these 2 point of view a lot. For example, when we try to later classify global this anomalies, Tahu anomalies, we actually will consider global symmetry first, putting space-time internal symmetry together, and in a way that we view the gauge group as just internal global symmetry group first, and then classify anomaly in this picture, and later on go back to gauge it to check anomaly cancellation. So we'll switch between these 2 point of view. And there are other examples familiar for people consider other biology arxiv anomaly, global symmetry current, actual not conserved due to dynamical gauge field. And there are also other types. So, and lastly, I just want to fix the next terminologies that when I say an anomaly, which we know these are the boundary phenomena, but we may say invertible as in my talk. Some people may include non-invertible anomaly, but we won't in this talk. And this is Zheyan class I already explained the local or global perturbative or non-perturbative anomaly. One can capture local one by Feynman graph. The global one cannot be captured by Feynman graph. And also the probe, we may say gauge anomaly, gravity or gravitational is specified as probe. So you should not be confused with this global, which means the non-perturbative property that the symmetry transformation or diffeomorphism that cannot be deformed from the identity. That type of global anomaly with this gauge, these are different adjectives specify different things. These are specified the probe field as internal symmetry coupled to gauge field, whether this gauge can be a background gauge or dynamical gauge. So these are the terminology. So just make sure you're with me. And we may also put other probe like chiral or axial symmetry, then this will be chiral symmetry anomaly. And the Bosonian-Fermiani background field, Bosonian-Fermiani, let's say the manifold graded by Fermat parity or not. And then I also mentioned earlier, this total on these background fields versus the dynamical fields. So any question for this? So we just fix terminology, so we won't be confused. I know. So for certain anomaly, if I mention, I should possibly put some adjective to describe what exactly which one we are discussing. But if it confused you, please ask again. So we are going to talk about these three topics. First is quantum criticality, shooting to the quantum matter seminar. And the second one is go to ultra unification. And the third one will synthesize, combine these two ideas. Okay, so I already mentioned the standard model, but right now we will look into one particular gauge group, the one that had mass Z6. Which is more restricted. And the reason we want to have that is that we want to embed this to SU5 or spin 10, the SCARF model. And that really requires this mass Z6 case. Other case cannot be embedded. That's a global constraint of Lie group. It hasn't been so clear to the older literature, but I think people are aware of this. But in any case, let me just write down the gauge group SU3, SU2, U1, hypercharged mass Z6. But we also add another X. This X is the B minus L. In the standard model, actually, this can be just a global symmetry. It does not need to be gauged. But let's put it together, just be safe. And we will consider it later on be gauged. There's still a choice that we can just consider as global. And this is a combination of B minus L and hypercharged Y. In a particular normalization, actually, some people might normalize hypercharge by differ by 6 times. We are considered integer U1 hypercharge. So these are the integer quantiles. You might need to divide by 6 compared with textbook, for example. And this number is given here. So the model here, we so far just added the Young-Mills term and also the Weil-Fermion spinner. And actually, in this part of my talk, the quantum criticality, I will include the 16 Weil-Fermion. And in the second part of my talk, I will remove it. So in the first part, let me just add it. So we have a 16 valve spinner per generation. And we don't consider standard model Higgs just for the simplicity. You can add it later, but we just remove the standard model Higgs. So we will not have a standard model electron weak symmetry breaking. We just consider nearly massless model. Any question for this? So if it's clear, then we can go to some other gauge group, put in SU3, SU2, and U1Y together. When we have a left, the doublet, we can put in that. Yeah.
I just want to make sure. So after you include U1X, the field you consider is no longer what people call the standard model? It depends, because different people put standard model differently. Some people will even remove right-hand neutrino. So you can say these are standard model SM-like theory. Okay.
This is still reasonable standard model. It's not, So people might remove this, and people may not add this. B minus L can be a global symmetry, yes. So you may not gauge it. But we just say that this can be gauged. So we put it here just to make the embedding clear. So I'll show you the embedding. So Pati-Salam has SU4.
Whether it's gauged or not has some consequence, right? For example,
yes.
The distance of another photon.
Yes. Yes. Let me discuss all the gut, and then you can ask again if you want. Let me keep going. So these are the model of SU4, SU2, SU2. So the SU2 has this left, the familiar one, and SU2 right for this. Originally, in the standard model is a singlet, but right now we put doublet. So these are overall Pati-Salam. So we will call this PS model. And again, this gauge group, they actually also have 2 choices, depending whether we have Z2, I think. But in this case, if we want to embed to spin 10 later, then we actually have this gauge group. We have Z2 twice. And that's it. So one thing you should pay attention is this pattern of putting some of the quarks and lepton together has a different way of putting. So these are PS model. Okay.
Oh, could I ask a question?
Yes, please.
Sorry, I think I need it explained to me. When you say times, when the multiplication between SU4 and SU2, for example, has times sub Z2, what does that mean?
Yes. yes, I didn't explain this notation clearly earlier. I think earlier I do show it, but maybe let me say it again. So this Z2 means this spin 6 and spin 4 share a normal subgroup Z2. And here we mark out the common one, which means they only keep the common one once, not twice. So
okay.
Yes. So that's the part of the center. Yeah. Part of the center subgroup. So this one has some Z2 times Z2 center. And this one, yeah, and this one has a maybe Z4, I think Z4. And then we mark out the Z2 normal inside the Z4 and the diagonal Z2 inside this Z2. That's it. So there are some common sum you can model. And again, the reason you can is because the standard model particle content is compatible. Actually, you can also choose not to model. And that's related to what the Eugene tried to ask. If we have a certain particle not compatible with some of the globally good structure, then we can rule out certain case. But we haven't found any particle not compatible with those choices. So there are freedom. You can choose to model the Z2 or not. Okay.
Yeah, thanks.
Thank you. So now let's have another way of putting. So actually, these are the Georgi-Glashow model. This is possibly the first one. And we have a phi bar from going this 3 quarks and this doubly, this 2 of this left-hand sector phi bar, and also this one 6 and 3 and 1, and also the dangling leftover neutrino is 1. So this one actually is not coupled to SU5. So the stereo neutrino standout is a trivial representation of SU5, but it actually coupled to the U1X, which is some facts. And you can put SU3, SU2 in some way nicely as SU2. Like if you write 5-dimensional representation, you can embed this nicely. But one clarification is actually the following. That's clear to the previous literature that actually SU5 and U1, the way to identify to the U5 group, actually they need to model a Z5. So SU5 is a Z5 center. And U1, you can choose different way of a normal Z5 subgroup. And this actually turns out to have a different way of viewing this U5. If you identify one of the Z5 generator, 1, 0, 1, 2, 3, 4, any of the group element as the generator 1 of the U1 charge 1, then actually it seems like there are several possibilities. And you can ask whether this identification between the center group element, each of them can generate all the generate Z5. You can identify this 1 with 1. Then which I will call U5-1. But it turns out that Georgi-Glashow model actually required to identify this 2, this Z5, this second group element 2 was this 1 of the U1. And these are the U5-2. So these are the subtle part. It turns out that the U5-2, this index U5-2, this type of Lie group can embed to spin 10, but U5-1 cannot embed spin 10. And spin 10 is a gauge group of the SO10 Grand Unification theory. So there are some confusing facts. But U5-1 actually can embed to SO10. And which is not the gauge group for this Grand Unified SO10 model. Let me also clarify, when I write the lower class is a Lie algebra, I'm trying to be very careful about global structure and local structure. Well, when I write capital case, I'm meaning the global Lie group. So for example, now U5-2 cannot be embedded to SO10, but U5-1 can. So they have some subtle relation discussed in all paper. Okay, so we kind of put things together. And now there's also one model, which I'll briefly mention today only, just the flip model. We can group 3 and the 3 of this, the one of the quark. Now, actually, it's different. Earlier, it's actually the D quarks going with the leptons, putting together in the 5-dimensional representation. Right now, it's actually choosing in the flip model, actually, it's a U bar and this doublet of the lepton. So flip model and Georgi-Glashow model is more like exchanging this D and U and also mu and E, and then going the 5 bar 10 one differently. So you will see now the neutrino right-handed is not outside the SU5 group of the flip model. And the gauge group structure is similar, but the representation identified differently. So the gauge forces are also experienced differently for those particles. Okay, and lastly, it's just putting every 16 together as a 16-dimensional representation of the spin 10 group. So when we say SO10 Grand Unification theory, actually we mean the lower case, Lie algebra, but the Lie group is always spin 10 because SO10 does not have a 16-dimensional spinor representation, but only the spin 10 has. So we have reviewed all the the gut we need, and we can put the gut forces together. And these are the Lie algebra generator. For example, there are 3-dimension SU2 and 8 SU3. These are U1, U1. And we are going to show the next few slides, just review a fact. Some people actually know, like Bates, they all paper actually mentioned this. We are going to say this fact just by showing you the graph, is that the intersection between the Georgi-Glashow and Pati-Salam actually naturally include the SM model that include the U1X. So not just the conventional SM, this Lie algebra, but also include additional U1X. Intersection in the sense that just try to find out the set of the Lie algebra that they generate minimally among them and intersects. And you can also consider the union, which means try to complete the Lie bracket and then not only contain the Lie algebra of each of case, but I also explore the whole structure. It turns out it will generate SO10 Lie algebra. We also check the global D group structure is compatible. So in a sense, we will see that the spin 10 gauge group indeed contain Georgi-Glashow Pati-Salam in some way, while these two intersections give rise to the SM of this gauge group. And here, next few slides just show the graph in terms of the algebra, like SU4 left, SU2 right, and SU2 left, SU2 right, and SU4. They have this algebra. Some overlap, always overlap with the SM. There's a different overlap for the U5 model, and like this of the Georgi-Glashow, and putting together these are the spin 10 of the 45 generator. So this fact seems interesting, because in the past, the high energy people might debate whether we should go to the Georgi-Glashow route or Pati-Salam route to go for the unification. The one I put is not just for the high energy scale, but we can put in the phase diagonal also horizontally. So there are quantum vacua parts we can put. Standard model will just be a neighbor vacuum next to Georgi-Glashow and Pati-Salam. So we are actually thinking this way. And we can also find appropriate Higgs field in the representation of SO10 or spin 10, because these are the boson, the gut Higgs, not the electroweak Higgs. And with appropriate representation, 45 and 54, it turns out it can have a suitable breaking. So in the dynamical gauge group, these are the Higgs gauge breaking. Although the gauge breaking may not be quite physical things for condensed matter people say in now modern terminology, but you can regard this as a symmetry breaking when we regard this internal symmetry as a global symmetry. So for a moment, we can just regard this as a global symmetry breaking by some condensation of scalar field, and we also discuss gauge consequence later. And with this condensation, turn out 45 and 54, they can go condense 45 representation go to GG, condense 54 go to PS. If you subsequently condense 54 or 45, you will go to SM, and which means if you condense both, you will go to standard model. So we would like to explore this structure further. And this 45 and 54 actually sitting in some 100-dimensional representation also for the SO10, which is 10 by 10 representation. And actually it's also part of the 16, 4 of the 16. So you can think about there could be some 4 fermion effects from spinor representation of this standard model coupled to the some 10-dimensional vector of the some scalar field. And then this pi of the scalar field becomes some 100-dimensional representation that we require. That part of this, we can have 45 and 54, take out some vacuum expectation value, and then trigger this condensation. So let's be more explicit in the next few slides. So the gut Higgs transition, which we're going to study, is that not just the model we write down earlier, and now putting the 16-dimensional representation with spin 10 gauge group, plus the terms I motivated earlier, this one here, is that there are some coupling between this bivector Higgs field, which is in the 10 by 10 dimensional representation of spin 10. Their symmetry representation is the same way as a fermion quartet term, not a bilinear, okay? And then we can introduce some Lagrange multiplier phi in 10 dimension. These are auxiliary scalar Lagrange multiplier without dynamics. The thing is that it try to introduce an interaction between this gut Higgs in the 100-dimension representation to the 16-dimensional representation. So you see the fermion bilinear coupled to the vector 10-dimensional a little phi, and 2 of the phi coupled to this 100-dimensional bivector. Bivector means there are 2 of the phi, 2 index. And when with appropriate God-Higgs potential that we can introduce to condense 44, 45, and 54, we can go to the Georgi-Glashow Pati-Salam model. So this model is not new, actually, in the sense, these are just Yukawa Higgs put in the framework, just try to say thinking about quantum phase transition. But much sooner, we are going to introduce Newton to make new physics in a natural way. Any question about this slide? So that's a potential I8, or we can 8. The V8, that 45 and 54, they could have a different quadratic and the quartic coefficient, and then you can condense, or not condense, some of them. And then let me just explain. For example, these are R coefficient for 45. If R45 is larger than 0, then this does not condense. And this model, for example, can go to SO10. And similarly, 54, you can also choose R45 to be larger than 0. So in this block, R45 and R54, both are larger than 0. The God-Higgs does not condense. And this will go to the spin 10 model or SO10 God model. If you condense the 45, and it will go to R45 smaller than 0, and you can go to Georgi-Glashow. But it turns out that there's a choice of a different VAF for the 45. It's more like a different symmetry breaking VAF of the same representation 45, which can choose to Georgi-Glashow or Pati-Salam. The Philip U5 model. That's also the model I review. So these are the possible routes to go explore the 0 temperature phase of this model. And we can also go from SO10 and to condense the 54 by flipping the sign of this R45 from larger than 0 to smaller than 0. And this axis, when you go down, you can go from a spin 10 model to this Pati-Salam. And if you condense both 45 and 54, you go to the standard model. So far we discussed the bulk part of the phase diagram, and these are 4D theory. So these are just portion of the phase diagram, which we are certain. And we want to explore more about the phase transition and ask whether there's something even more interesting in the critical gapless region. In particular, we are going to modify the conventional, the SO10 coupled to this God-Higgs. These are kind of still conventional, except that we kind of introduce certain God-Higgs potential. But the new thing we are going to do is modify this and adding a waste terminal Witten term. For the reason it will be clear in the next few slides. Yeah. Any question? So
could I ask? So this 45 and 54 give you the freedom to break down to these various intermediate phases, and then do they? So for example, they can get you either down to SU5 or Pati-Salam, and then once you get there, do they also these same fields provide the Higgses to break you further down all the way to the standard model and down to SU3 times U1 electromagnetism, or are those will those require additional fields?
Very, very good question. Actually, I cannot recall now, but actually we are not going there for today's talk. It's a good question. We may need to add another electrical weeks. So your question is asking whether 4554 or its subsequent branching rule provides the SM breaking. I forget. I can check easily, but that's a good question. We are not going there because we are kind of explore the gauge group structure for above the electron weak Higgs scale.
Okay.
So you are thinking about this 150 GeV scale, and here we are kind of thinking above and also at the quantum phase diagram. And that's a question that I can address. After my talk, I can check.
Okay.
Very good. Thanks. So Layson was asking the electron weaks, and which we don't add here. We just consider God-Higgs, and there's a good clarification. So the phase diagram, if I just focus on not the fleet model, remove that, and looking at this two-dimensional plane, a slice, for example, choosing the VAF condensed to the 45 one along like this plane, then this diagram looks like this. And these are a quantum phase diagram, depending on the
is it just me or is Juven frozen?
I think it's Juven.
Let's wait a few seconds, see if he will come back. Hey, Juven, are you back?
Yes, somehow I don't know why it happened, but let me reshare the screen again. Sorry for not sure. I didn't do anything, but I think just try to the purpose there, the interruptions try to bring you attention again. So now we already present this model one. Right now we want to add some topological term built from God-Higgs field. And the claim later is that this God-Higgs will saturate some W2, W3 Stiefel-Winnie class anomaly. And for some people who may not be familiar, don't worry, I will explain. But for people like Tong, he knows this. These are the anomaly classified in certain symmetry group, including, for example, spin 10 internal and space-time spin group. And they share some Z2 Fermat parity in the sense of like space-time internal symmetry locking. And there's a Z2 generator for that. And these are the Z2 class. And you can think these are some invertible topological phases classified in 5 dimension. And that captures some 4D Tahu anomaly of the SO10 group or actually precise spin 10 group. We want to consider the possibility the whole phase diagram can live on the boundary of this term and whether they are new physics. And this is a natural choice we can do.
Sorry, Juven, maybe I'm confused.
Yes.
I thought you want the gravitational anomaly to vanish.
Yes, very good. Very good question. I'll go there. Very good. So the thing is that for the moment, right now, let's not gauge SO10 and spin 10. So these are global symmetry. And we will consider whether spin 10 is gauged later. So okay. when the spin 10 is still global, there's no harm to just consider a 4D theory with this 5D term boundary.
Okay.
And what's on worry is something we will address later, because once the spin SO10 is gauged, it has Fermat parity sure, and there's something wrong with the 4D and 5D decoupled system. You cannot just leave in the 4D theory on the 5D boundary. The short message is that once spin 10 gauge, in this second model, the spin 10 gauge field can propagate to 5D bulk. And it's a way to explore higher dimension if that model makes sense. And these are the features for that model. At this moment, let's pretend to be condensed matter people thinking about this as a global symmetry. And we will gauge later. So for Chong, he's a pioneer on this type of works on deconfined quantum criticality. Chong, Yi-Zhuang, and Yi-Zhuang and Liu Jun, people local here. These are proposed by Sento et al. In 2013. They are looking at some phases, compared with the phase diagram we are looking at. They are looking at 2+1 or 3-dimensional space phases of spin system, and this spin has spin 1/2. Degree of freedom, a bosonic spin 1/2. These are internal spin 1/2, not confused with the Lorentz spin, okay? These are internal spin 1/2, internal symmetry spin, 2-dimension representation. And then this spin degree of freedom can form near order break SO3 rotation or VBS breaks, for example, the U1 of discrete Z4 lattice translation or C4 symmetry. So these are different symmetry breaking pattern. So these are break SO3. And there's a Z4 U1 SO2 in a continuum, and this one is breaking SO2. Sorry. So it's similar in some way in analogy to the case we have, except this case is more subtle because we don't have a separate product group between the two, but we do have a SO10 which contains SU5 and SU4, SU2, or spin. Let's just try spin 4, spin 6 times spin 4. So we can ask, are there some interesting phenomena that people study co-deconfined quantum criticality? And that means that some Landau order on two sides, you don't see some additional emergent deconfined degree of freedom, but only see at near the critical transition. In their case, actually, it's a critical point because there's only a single point phase transition in this tuning parameter. And also in this diagram, these are a finite temperature diagram. But in our case, in the BSM, actually, these are the whole zero temperature phase diagram. And we actually also don't have a DQC point, deconfined quantum critical point, but a deconfined quantum critical region, because the nature of the deconfined theory, especially in one of the model I will introduce in the next few slides, the U1, deconfined property is different from the U1 in 2+1. So we have a deconfined quantum region, but the nature is similar. And in their model, this model is also considered SO3, SO2 as a global symmetry. So for the sake of a comparison, just thinking about this SU5, spin 10, and spin 6, spin 4, all as a global symmetry first, and we can consider dynamical gauge them next. Any question for this? So the analogy here is that it could be possible that there's just a boring Landau-Ginzburg type of phase transition, and then the Neal order and VPS shouldn't meet, fine-tune at one point. Then the phase transition should go like this, and famously, either they overlap or they have this finite region that they don't have a Landau order. And similarly, if I don't really tie this theory to any control anomaly of W2, W3, the phase diagram may not be so tight. And because of Tahu anomaly I'll introduce for the theory, this SO10 group, there's additional gapless degree of freedom enforced by the Tahu anomaly, or additional TQFT. It must be some non-trivialness because the Tahu anomaly must be saturated by something. So these are the analogy to the phases. Okay. Any question?
Juven, just make sure I understand. So on the left diagram, it looks like this. Are you basically just tuning the two Higgs masses to?
Yeah. Yes. That's correct. So I'll tune the two Higgs fate mass, but now I also need to aid not just the Higgs mass term, the God Higgs potential term, but also the WZW term. And with that, there's additional effects.
Oh, okay.
But this, yes, but it's indeed tune the Higgs mass. So these are the one I draw R45, the mass term, larger or smaller than 0. Yes, indeed. Yes, correct. And also the statement about the fine tuning, let me just say, for example, if you want to go from GG and PS, suppose there's no such a critical region, the deconfine critical region. If you go to GG to PS, go from GG to PS, you might either need to go through the SM, like go in this here, or go through the SO10. Unless you have a fine tuning in a two-dimensional parameter space, you fine tune to go through this point, and you can go from GG to PS. But these are the model first, if that's the case. But the second model is that actually, if there's a critical region, you can moderately go through GG to PS if you go through this critical region. So you can think it's more GG and PS more connect to each other through the critical region.
Sorry, when you say critical region, exactly what do you mean? You mean an intermediate CFT or?
Yes. The candidate phase for which I will construct. The candidate phase is certainly depends on the detail of dynamics, and which we don't have we don't really know. But we can do the analysis as much from anomaly matching and also from construct the field theory. But I will propose that possible low energy theory as possible gapless theory, such as CFT.
So you're proposing that entire circle, that entire disk may be a stable CFT.
Yes.
Okay. Yes.
And yes, so that's the second model aiding the WZW term, which I'll aid. I haven't said which one it is, okay. But the first one is remove this critical region, and there's just the usual this. Okay, so there are two models. So we so far already just built on the first one. Okay, now we are going to aid this WZW term, which is topological term, and these are the term built from the God Higgs term, and for condensed matter people might call intertwined order. So these are the way to do this is we look at the topological defects of the symmetry breaking of one of the order parameter to carry the symmetry charge of the other order parameter. So we have a 45 and 54 breakdown to GG and PS model. Then the breaking is from SO10 to the U5, and we can look at the defects. And this defects has a target manifold of a coset of SO10 mod U5. And if you look at another 54 Higgs, we can also have the breaking and such that the target manifold of this order parameter space is SO10 model, SO6, SO4. Here we only consider the bosonic scalar field, so we are not worried about the spin graded by the Fermat parity. So these are just bosonic part of the symmetry group. And to construct such a topological term, actually we didn't look into the defects classified in a semi-classical sense by homotopy group. So we can look at homotopy group data pi of some dimension. And in particular, the two-dimension pi2, which means a sphere wrapped around some spatial region, classified some a monopole. The monopole is not the gauge monopole here, it's just a singular configuration of the two-dimensional sphere wrapped around the three-dimensional space. This pi2 for this target manifold or coset has a Z class, and this pi2 also has Z2 class. The thing about construct this topological term require to choose a dimension such that one of the defects dimension pi of the one of the target and the other one, this dimension A dot together need to be a total space time dimension, which is 4. So for example, we need to combine 1 and 3 or 2 and 2 and choosing a defect in some way. It turns out that there's only one choice looking at homotopy data is pi2, because this one, like this one paired with this one, doesn't work. I don't know whether it's followable, but let me just say it anyway. So there's actually a subtle check. Yeah.
It's probably not important, but what about 4 and 0?
That's a good point. Maybe it's possible from this semi-classical analysis, but it doesn't match the W2, W3 anomaly. So that's also, so we have something like this W2, W3. So these are like B prime, this two-form field term.
Right.
Yeah, for someone he certainly knows this construction for the DQC in 2+1. So these are similar analogies, just try to build out topological term. So it turns out that these are the terms you can look at. And with that term, it means that if we look into 4D space time and with 3D space, there's some monopole of this the God-Higgs potential. So these are singularity of the God-Higgs configuration, not confused with the gauge monopole of the gauge group. That one we don't touch, because that one with 16 biofermion per generation cannot carry anomaly of this type. So we are building an anomaly by the God-Higgs. So thinking about the standard model sector or the God model sector has some good anomaly cancellation property, but the God-Higgs can have a locking between 45 and 54, some locking, and that locking will be the interwine between the topological defects, and such that the monopole of the 45 and 54 living in 4D, if we extend to 5D bulk, which will be a wall sheet, and this two wall sheet of the 45 and 54 can form a two-dimensional submanifold, and they can have a non-trivial linking. And this linking, if that linking have capture a non-trivial link invariant and with a non-trivial partition function evaluation with the statistic sign -1, then that's what we want. And the claim is that aiding this term of the BDC or BDB prime, just two form or second cohomology class built from a more precise cohomology construction out of this target space, you can give rise the statistic we want. So this will be a new term we aid. So these are new model aiding this term, the second model. And then with that aiding this term, the claim is that we can have Higgs sector, God-Higgs sector, capture this anomaly of W3. And the Higgs, God-Higgs, actually these are God-Higgs, should be viewed as the 4D boundary modes now as the 5D bulk of this invertible TQFT. But what someone asked is a good question earlier, said that, but he thinks that shouldn't this anomaly should be canceled just in 4D alone? It should. But if that theory, 4D really required to live on 5D bulk, then there's a consequence, which means when the gauge field or gauge group is gauged in the spin 10, the full spin 10, then actually this theory is a coupled 4D 5D system. You cannot really think these are 4D theory live on the boundary. They are highly correlated, entangled in the sense the spin 10 gauge field can propagate to a 5D bulk. In a sense, when we define this W2, W3, this is actually a mixed gauge gravity type of a Ma2 anomaly. They actually gauging the spin 10, also gauge the SO10 bundle and its connection, and that whole term to be sum over. So these are not really a gapless bulk once the not a gap bulk, but possibly a gapless bulk when we gauge the SO10. Yeah.
Actually, okay, this question might be a little bit more detailed, so if it's
no worry,
feel free to ignore it. But I understand why W2 of SO10 is same as W2 of the tangent bundle, but why is that also true for W3?
Yeah, very good. So these are just some relation between W3 is actually SQ1 of W2 TM. SQ1 is like 1/2 delta. So there's some constraint between the two. Yeah. Once that relation holds, this relation also holds.
I see. Okay.
So, yeah. So the bundle constraint is that case. Okay. And there may be some additional modification when you take SQ1, maybe with time reversal background, there could be additional W1 term, but in the case, we don't really consider time reversal here. So W2, taking this derivative, STINROD SQ1, or 1/2 delta of this derivative, it will be W3. So there's a constraint between the tangent bundle and gauge bundle. Yeah.
Yeah, great.
Thank you. And that constraint is due to the spin times spin 10 Marzito structure, which is related to the spin space-time and the charge spin 10 spin charge relation. So I will need to quickly summarize the statement now is that so there will be additional deconfined degree of freedom in the second model, and it's analogy to DQCP. And once we gauge the spin 10, there's something about the gauge enhancement into the spin 10 region, you can propagate to 5D bulk. But when you are restricted to Georgi-Glashow standard model, as we are, or Pati-Salam, we are restricted to 4D boundary. So that's also an interesting feature for this model. So only when we are near the critical region, when the gauge field is enhanced to spin 10, then you can go inside. There's a secret channel go to the 5D bulk. But if you only live in the standard model group, then you are just confined or restrict to 4D theory. So only when possibly go to even higher energy, or maybe just some way to go to this critical region, then you can go to the 5D bulk. And the thing, next few slides, I will just summarize that there's a construction of this WCW term we already mentioned, but now we also construct possible low energy realization at IR as a deconfined U1 prime dark photon like a new gauge group gauge field as a low energy realization with WCW term. And it can be checked by some method or by this new SU2 anomaly method. And these are the next few slides. But before that, I want to make sure whether you have any question, and can I still go on for maybe a few more slides? How much time do I have? That's a question. I think yeah.
Technically zero, but feel free to go on, and people should feel free to leave if time comes. But
no problem. So no problem. Thanks. So let me ask: is there any other question before I go on? So the next few slides will be technical to construct the. Maybe I will just be very quick, just show that this critical region. That's what I'm going to do. And then after that, I'll go to summarize actually the other thing I want to mention, but in a very quick way, because I think I'm out of time. Unless people are really interested, I can certainly take as much time, but I don't think it's good. Just so yeah. So we have this phase diagram, and there's some critical region, and the situations. The proposal is that possibly there's one 4D theory like QED prime with a new U1 prime gauge forces, and such that this gauge theory, U1 gauge theory, coupled to fractionalized degree of freedom, which we call fermionic parton. And this fermion is also some spinner, but it's Dirac spinner, a Dirac spinner, and 10 of them in SO10, 10-dimensional representation. And there's a natural way to couple this spinner with 54 and 45 God Higgs field. And the claim later in the next few slides just try to say, once I integrate out the gapped theory of this fermion parton, actually I can also reproduce the BDC term. And also I would like to show that this fermion parton theory can give rise to the same anomaly of W2, W3. And that's basically, and this U1, the U1 prime gauge force is actually neutral under the spin 10 or SO10 gauge group, but it only carries the charge 1 on the U1 gauge boson, or the U1 prime, the dark photon. And the phi, capital phi, is the 10×10 of the SO10 God Higgs field. And there's some way maybe you can think some people in condensed matter, we call the fractionalization, which means we try to fractionalize God Higgs as a boson to parton, fermion parton, and these are the fractionalization. But we need to check they have the same anomaly.
Sorry, Juven, let me make sure I understand your exact statement. The statement is you have what 10, but it is what? So this Dirac fermion is in the vector web of SO10, and when you gauge the U1,
Yes.
it has the W2, W3 anomaly.
Yes, the whole series has W2 right now. Yes, and the gauge U1 is the deconfined U1 near the critical region.
Yeah, this is the part I'm a little bit confused. So that W2, W3, once you write in terms of the tangent model, that's a gravitational anomaly. So why does it have anything to do with a global group like SO10? Yes. SO10 here is global group, right, for you?
Yes. So I need to explain them a few slides. Yeah, this is a good question. Okay, but before
if you're explaining that later,
okay, great. So I'm going to explain that. But before I go to the technical part, let me just say one more thing. These are the Dirac parton, which is Dirac fermion. They carry different representation of SO10, which I say the 10-dimensional one. And you should decompose, for example, in terms of phi, in phi bar of SU5, and thus you can read the quantum number out of the SU3, SU2, U1. So in some sense, they do couple to or carry some quantum number of this SO10. And however, in a phase which we will explore in the region of so-called the standard model phase, we live in the phi 45 condense, and actually this will gap the parton. Sorry, gap the parton. Where do I have with the either we go to Georgi-Glashow, Pati-Salam, or same model with those God-Higgs condense, you will see this 545 and 54 coupled to this parton as a bilinear way. So this non-trivial, non-zero VAF can give mass to this quantum parton. So if we are in the region that just try to connect to the real world, if that VAF is large enough, it can give a large mass to the parton. So we will not be able to see easily at low energy of our SA model. So these are the parton content. Okay. But there's still a U1 prime dark photon decouple and remain maybe as something like a cosmic background radiation, if you want to think what might be the consequence. So we are mostly focused on like a more theoretical or formal theoretical issue, but here is just some connection if you want to relate to maybe the phase in this region. If you really want to make a connection to a real world physics, there might be applications. But there's actually several issues I need to address now is like just what Tong said, why is this internal, why does this carry gravitational anomaly? And also in the sense, if this fermion can be gapped, for example, why do we capture even this anomaly index? And the question, in the case of, in the case actually, whether it can carry anomaly index is related to the fact, first of all, whether the spin 10 can be broken or preserved, or is broken or is preserved. So certainly we can break SO10 and we can give mass. For example, like 45, 54 will give break SO10. So it's not an issue. But actually it's possible to write down some bilinear thermal mass term and then you can gap it. So there are some subtle issues I want to address now. So let me just summarize what we are now. We are proposing the model of the modified SO10 model. And with this, not just the God-Higgs potential, but also this topological term. And then now the low energy physics we want to say is that it's possible to have an IR realization. It's not just this one is possible. There could be others, but we are proposing this might be most related to the deconfined quantum criticality. And this model has what we just earlier showed. And let me just say a few evidence why this model gives rise to the WZW term. So one thing is that you can derive this 4D model on the boundary, on the domain wall between the 5D bulk of this theory. So the 4D theory is this Dirac fermion of this Cassi fermion in spin 1,3. While the 5D theory has another fermion, and which is actually full component again, but actually I need to double the spectrum somehow because the domain wall theory fermion degree of freedom actually is half of that of the 5D bulk. And this fermion is also called Cassi, sorry for this, using the same notation. But the claim is that if you write down these fermions, there's other than the familiar gamma matrix of 0, 1, 2, 3, 4, or maybe gamma 5, sorry, just gamma 0, 1, 2, 3, and 5 for the 4D and 5D, there's additional doubling spectrum of the fermion can introduce two more gamma matrices, like gamma 5 and gamma 6. And there's a natural way you can couple to the B and C field. And the claim is that when you integrate out a gap phase of this fermions, actually, it will give rise to the BDC term, also in the 5D bulk. And the domain wall theory produced this WZM term. So at this stage, you find a connection how the fermion-parton theory might relate to the BDC, and that can capture W2, W3 type of anomaly. And this BDC type of anomaly can also be checked, for example, by method that the McGreevy and other collaborators actually they kind of work out this BDC theory types. But the next one is even more precise, is that how do we match the W2, W3 anomaly? So there are a few subtle facts. First of all, is that the Dirac spinner, the C, is the 2L, 2R in spin 3,1. But this is also in the internal symmetry of SO10, 10-dimensional one, and the U1 prime, a charge 1. And now, a few facts is that in order to realize this C compatible with spin 10 Grand Unification theory, this fermion content is not quite compatible with this gauge group, because the spin charge relation in this one does not compatible with the new Dirac fermions, this fermion-parton. So the way to understand this or to resolve this is actually there are two types of fermion parity. One is the 16-dimensional representation fermion for the standard model or the gut model of the fermions. The other is the different fermion parity for this C, and there are two fermion parity. And this type of structure actually was also studied in other literature in string theory. For example, this Yuji Tachikawa studied similar kind of structure. And in our case, we require double spin structure, just two fermion parity. If you combine this double fermion parity D-spin structure with the spin 10 and U1 prime gauge group, the full modified gut model require this structure. And certainly later on, we want to gauge U1 prime, also gauge spin 10. But if you just regard everything space-time internal symmetry, these are structure. And towards the end of the question, say why this theory can actually capture the W3 anomaly if they can be gapped. Then actually there's also a subtle fact about we need to actually protect we need to introduce additional symmetry to protect forbid the quadratic mass that can preserve the SO10 or spin 10. So there's some discrete symmetry actually can protect. First of all, the U1 prime, the imaginary U1 prime can protect forbid the Marana term, Marana mass term, Marana mass-like term. And the CP or T prime, which we define, these are different CP and T symmetry for the parton theory, not for the standard model theory. They can protect other type of bilinear terms. So with all these possible discrete symmetry protections, actually we can forbid any possible mass term to gap the fermion parton. Then we can ask what are the anomaly index it carry. So the method we use is.
But why do you need the time reversal? I thought that not require.
Not for the SM. These are the different time reversal in the parton theory.
But still,
just for other discrete symmetry, I think that's just the way I put it. Actually, I don't have other way to forbid those terms. It's just like it seems there's some additional discrete symmetry in order to protect. Maybe there are some other construction possible, but at least for this 10-dimensional model, it seems a 10-dimensional representation of SO10, it seems like these are the most simple way to put. Yeah.
W2, W3 anomaly be well defined even if you don't have any time reversal at all?
Yes, but this W2, W3 is just definable within the spin times spin 10, right? So I do aid possible additional symmetry in the parton sector. I don't affect the SM and Gauss sectors. So it won't affect the calculation for the cobordism invariant. That's still there. This anomaly is still there for the whole theory. But because I want to capture the anomaly from the parton theory, that also carry the internal symmetry SO10. I think that's the way that we can come up with. Yeah, these are subtle facts, actually much more subtle than usually I don't discuss this, but since I think this will be interesting, I just mentioned.
Okay. Right.
Yeah, but we can discuss later more about this. So the next few things is that we will be able to rewrite the internal symmetry for the SO10 and U1 prime in some way to enlarge. And the reason we want to do that is just try to identify the WW3 anomaly. But the trick we want to use is we go to some group involving SU2. What we know is that this anomaly of WW3 related to the spin 10 group and the SO3 group, actually they kind of can embed into each other because spin 10 includes spin 3, and which means that it includes SU2. So we would like to use that tricks. So there's a set of rule, Lie algebra, this there's a branching that try to first we pull up to a larger group and then go down to another new internal symmetry. And the punchline is that there's a SU2 prime, double prime, that we can identify the new SU2 anomaly. But the thing is that there's a full component of SU2 prime, which means like iso spin 3/2, or just internal full component of this SU2 prime. And that one, based on the previous work we did, is that it carried a new SU2 anomaly if it's a 4-dimensional representation. And these are in contrast with like Witten anomaly 2-dimension or 6-dimension carry the Witten anomaly. So this one carried the SU2, new SU2 anomaly, and we can relate them back to the spin 10 anomaly. While the other sectors we separate, it doesn't carry anomaly index. So we identify that there's a W2, W3 anomaly of gauge and gravitational mixed anomaly type. Right. Let me just contrast one thing because Chong also worked on this, but the different about the anomaly we look at, these are gauge gravitational. I think Chong and other people, the type of anomaly they study, for example, in QE for fermion electron dynamics, that one is actually more like just pure gravitational anomaly of WW3TM. So there is no additional bundle constraint to the internal symmetry groups. So these are pure gravitational type of anomaly. But here we do have a mixed gauge and gravity type of anomaly. Yeah, so based on several checks, I think I try to say one is like domain wall theory and integrate out, we can get BDC term. And also based on anomaly index, I think there are some pretty much evidence to show that these are a possible low energy realization. So far, I think we kind of say that introduce a picture like there's a quantum vacua tuning parameters, especially using the GAT-Hicks, we are able to tune away from SM model. And there's a Georgi-Glashow nearby and Pati-Salam model, PS model nearby. And we are living in some region near the critical region. And there's a choice whether we want to consider conventional SO10 or whether we want to add a new topological discrete class of the WW term. And the consequences are different. There will be a new additional deconfined degree of freedom of U1 dark photon U1 prime if we add this W0 term. Okay.
Juven.
Yes.
Maybe go back one more slide.
Yes.
Maybe I'm a bit lost here. So let's make sure what the statement is.
Yes.
So here the system we are considering is the system a bosonic system or fermionic system?
Okay, it depends what you mean by bosonic fermionic, but fermion parity will be important. So I think it will not be easy to just say bosonic because we do require spin with fermion parity -1f and identify was part of internal Z4 center of the spin 10. And in the theory, just for a second, in the theory that the spin 10 is regarded as a global symmetry group, these are indeed contain fermion parity. So there's a Z4 center, and this contains Z2F fermion parity, and these are the center.
So the theory has a local operator that's fermionic.
Yes, if you regard spin 10 as a global symmetry. So fermion, there's a gauge invariant, there's a fermion operator, yes.
Okay.
But once you gauge the spin 10, then it's bosonic.
Yeah. So suppose I do not gauge the spin 10.
Yes.
Then suppose I just don't have the spin 10 symmetry at all. then this W2, W3 TM anomaly in the fermionic system is just trivial, right?
Yeah, I think that's right.
Yeah. Now the statement is, if I further have a spin 10 symmetry such that the fermions are in the fundamental representation, then this W2, W3 TM is not trivial, and furthermore, it's equal to W2, W3 of the VSO10. Is this the statement?
Yes, but you require fermion in certain representation, like in SU2, spin 3 or spin 10. For example, if you only add a U1, then I don't think there's such, I think there's no such term. Like spin C, there's no W3.
I mean, U1 doesn't have W3.
That's right. That's right. Yeah. So so it requires certain internal symmetry to make sense of your statement. But for spin 10, yes. If you consider, yeah.
Thanks.
Yeah, I think. Yeah, now I understand my confusion. Yeah, thanks.
Right. So maybe let me say my way is that the usual. Sorry for not showing this, not explained here. I was so if you consider the usual SO symmetry group, that's the W2, W3. There's a Z2 class, and these are W2, W3 TM. And if you try to move this, pull back to some group, including U1, that's a spin C, and that's what the Chong and others are doing. This is actually zero. There's no such term. So you can think this gravitational anomaly is trivialized. But if you pull this W3 TM to SU2, spin times SU2 minus Z2, sorry, then it will become a mixed gauge gravity anomaly, such W2, W3 TM, and the SON bundle will be constrained with each other. So that's the thing. Yeah, these are the way I understand their work. Is like the gravitational anomaly is trivialized in the spin C structure, and you can construct, for example, Z2 gauge theory if you pull back to spin, or spin C to construct all fermion electrodynamics. But these are all gravitational anomaly theory. And in my case, actually, in our case, actually, we pull back to, for example, like this one, but it will change the gravitational anomaly to mixed gauge gravitational anomaly, and there are some bundle constraints between the internal and the space-time symmetry. I don't know whether, yeah, I try to explain what I think.
Yeah, that makes sense. Yeah, thanks.
Yeah. So these are the subtle parts. These are very similar to what you guys study, but not quite, because you guys are gravitational, pure gravitational. These are mixed gauge gravitational. And you can just list down the SO compared with spin or spin C. These are zero. Okay. And for other audience, just let me just say, if you consider spin times SU2 with Z2, there's only one Z2 class, is the old Wheaton anomaly. And other one actually it can contain Wheaton anomaly and new SU2 anomaly. Okay, so these are the anomaly classification. So finally, I think I will just use 2 or 3 minutes, maybe before 5 p.m. I'll finish. It's just that so far we introduced a deformation class labeled by a cobordism invariant, this invertible TQT W2, W3, and we have a choice to choose P, this level Z2, to be 0 or 1. Conventional way is just choose 0. So the new model we build is choosing 1. And now, sorry, yeah, you can choose 0 or 1. Anyway, and in the next second part, actually, what I was going to say is that you can introduce a different deformation class, which is a Z-sitting class. So you can relate this to more or less like these are 4+1D or 5D version of topological superconductor protected by some internal symmetry X related to the same B minus L symmetry that I mentioned, which X squared is -1 from non-parity. It's similar to the 3+1D topological superconductor protected by time reversal square equal -1. So they are related by some Smith homomorphism map, but that's just a way to relate 5D and 4D theory. But this will be an invariant that will play a role because we have a choice to remove right-hand neutrinos. And you can think what we are going to do is moving around this vacuum by putting the theory on the boundary of this 5D term. And then controlled by this data, then there are some restrictions. What are the vacuum we can move, what we cannot. So these are two data, Z16 and Z2 data. So along the line of deformation class of quantum field theory, for example, like advocated by Cyber. So these are second part. But this story I already get it. The one major thing is that the right-hand neutrino indeed carry some gravitational and mixed B minus L anomaly that previously earlier question they were asking. But you can regard this anomaly as a total anomaly, and that's what he was asking earlier. But some people might say maybe we should just cancel that by 16 biophermal. That some people may want to choose right-hand neutrino, or maybe we can break B minus L and maybe break it onto discrete subgroup. And and if we summarize a conventional law, basically it says that just what I mentioned, total anomaly or maybe APG anomaly with gravitational instant on background U1 B minus L is not conserved, or maybe A right-hand neutrino and they put it very massive, and this X symmetry is somehow possible important. But what can we do? What else can we do other than conventional way? So the thing here, the second part is just say that maybe we can still ask, for example, if you add like if you extend the standard model, and then if you want to ask when you consider possible other higher dimensional, 5-dimensional, sorry, this contains the dimension of the energy of an operator, 5-dimensional, 6-dimensional operator, we may be able to break U1X down to some discrete subgroup. And then we can ask whether this discrete subgroup actually give rise to different anomaly cancellation. And this is a logic that later on I will say that it can give a nonperturbative global anomaly. And the punchline is that there's a discrete Z4X, this symmetry was mixed with anomaly with gravity. It's more like a U1 and gravity squared now becomes Z4 and gravity squared. And these are Z16 anomalies studied by many people. I think even as John Morris earlier, he also studied this anomaly. And I think I will skip some of the summary of anomaly cancellation. The punchline here is that once you do a calculation of anomaly cancellation, or this checking the anomalies, you'll find out that only the Z16 carry the anomaly index if you put in the 15 biofermion per generations. And that logic is saying that if you look at all the biofermion with charge 1 on the Z4, actually they are all the 16 biofermion there, and including the right-hand neutrino, they all carry an index 1. So they all can carry a charge 1 on the Z4 and carry the index 1 in Z16 of the Z16 anomaly. And that logic, what I would have to say is that suppose the Z16 anomaly is not canceled by 15 biofermion, as we say, then there's alternative story. And these are along the line what the quantum matter people try to explore anomaly cancellation by exotic phase of matter, like surface topological order on the boundary of this topological invariant, these 5D terms. The assumption I make is just the few of them. You just say the standard model gauge group and the 15 biofermion per generation. But the most crucial assumption is that suppose this discrete B minus L somehow is important and suppose it's preserved, not broken. Then this requires knowledge to say all the global symmetry should be gauged. So this symmetry should be gauged at some high energy. Then the anomaly cannot be just be a total anomaly, not canceled, but should be canceled. Should not be just an indicator for anomaly, but should be canceled by something. So that leads us a proposal to adding new sectors, which, for example, include surface topological order proposed most earlier, maybe by Yi-Zhuang and Central, and these are related to topological Green-Schwarz mechanism, cancel the Z16 anomaly by adding new sectors of TQFT, preserve the Z4 as well. Or include a 5-dimensional invertible TQFT just as one extra dimension, or just break. Also, conventional way is possible to also break the symmetry, but these are more boring. And it's also possible to have a Z4 symmetry preserving CFT. So these are just words, but give you a direction. Say the high energy phenol might have contain those new exotic excitations of gap objects of lines and surfaces, or even gapless CFT on particle physics. And the picture of this conventional series, like standard model, what I drew a few times, like these sectors. And the new sectors is like something people dream about, but they could be there to cancel the global anomaly. And there are some constraints about this anomaly cancellation to control the gap TQT I was skipped. And there's also some statement how to cancel the anomaly in the spin deformorphism and Z4 X, the spin minus cell type symmetry, internal symmetry transformation, and you can write down a deformorphism and gauge invariant hat integral, including the gap sector of CFT sector. In my paper, I mostly focus on control gap sectors. But putting this together, actually there's one that has comment is that we can say a few words about neutrino mass in the sense usually people use quadratic mass, but in a sense if we introduce this gap TQFT or CFT sectors, we know that this gap of the TQFT sector is not quite from the quadratic mass, at least not from the original fermion. Maybe you can have a dual description to introduce the TQFT, but these are different things. It's better to think these are the interaction way to generate mass. And if that's the case, we can revisit the question of a neutrino mass. And one thing about the possible neutrino mass, other than write down a quadratic seesaw type mechanism to push there's a left-handed neutrino with mass eigenstate such that it's a small mass compared to the Dirac mass scale, and push the other high energy eigenstate to the Gauss scale. These are the conventional way. We can consider an energy scale of something like TQFT gap. Yes, and that TQFT gap is some size, and then it could be somewhere below the Gauss or Planck scale. And this gap is like possible like superconductor gap of some topological theory. And it's natural to ask the topological defect traps at this TQFT. If you solve the zero modes of near the defects, there's some zero mode spectrum, but there could be additional energy subgap near the core of the defects. So I hypothesize the possibility to think about neutrino mass might be another way is that you can have a left-handed neutrinos, which is the weak eigenstates, and travel in some topological defect background, and then interfere with the zero modes. There's some interference, so might relate to neutrino oscillations. In addition, there's a topological defect subgap. This also generates a new scale, and this scale can be analyzed, for example, by the usual condensed matter way, the superconductor gap square divided by some higher energy scale, like Fermi energy in condensed matter is a small energy gap. And we can do similar analysis, taking the TQFT gap and do this analysis. I think this also generates a new energy scale. Certainly it would be nice to carry out the detail, and I'm also thinking about this along this line, try to do this calculation. And I have a report this long ago in 2020 in a string seminar. I think some of them get excited and some of them didn't get what I say. But anyway, but finally, just we are really putting not just the familiar forces, but we think there are some topological sectors or topological force matter, possibly also include in the unification in play some way in this deformed quantum vacuum. And with this together, we just put everything that we have a deformation of quantum parameters, including earlier Georgi-Glashow, Pati-Salam, but also moving between 15 and 17 value fermion. So the whole logic of this ultra unification should be something that you can control a critical region of all these phases. I haven't have a full model for this, for sure, because it depends on what you're going to deform. But I explore part of phases, including TQFT at low energy, and including the Georgi-Glashow, Pati-Salam. And it will be nice to really understand all the possible phase transitions and critical regions and low energy phase. And with that, we can summarize the deformation class, and they are labeled to control this parameter. And I think I will just end here, is that we basically give two classes, the Z16 and Z4 in my talk. And there's additional things I'll mention in my paper, but I don't think we should go further. So thank you very much for your attention. Thank you. Thank you for your patience.
Thanks, Juven, and thanks everyone for staying this long. Actually, a very quick question. Do you have a simple example of the kind of TQFT that can match the anomaly of the right-handed neutrino, like some Zheyan gauge theory type of thing, or what?
Yes. So I didn't go to a detail, but let me just say there's obstruction to match the nu equal to 1. You know, you're familiar with the 3+1D topological superconductor. Any R class still can have this 2+1D TQFT preserving the T square equal to -1 of symmetry. But in the case of this talk, we have a 4+1D bulk and 3+1D boundary. and with this x squared of B minus L symmetry minus 1F, and there's obstruction. For example, in Cordova and Omori's paper, they say that it's impossible to construct. Something's wrong with my pen. It's not possible to construct the gap TQFT for the R class, preserve the symmetry. But you can construct by symmetry extension method, which me and other people did. You can construct for the even class. So yeah, so there's obstruction. I think you are asking
what is even or odd classes? Like what decides that? I mean, for the standard model, does that depend on which Q you take or what?
It depends on how many right-hand neutrino if you want to add or remove. For example, if you want to replace one right-hand neutrino by a TQFT sector, that's not possible.
I see.
But if you want to replace two right-hand neutrino, which by form some doublet of the two vowel fermion, then you can replace that by a TQFT preserve this level. Yeah, so that's an obstruction. It's surprising to me because in the 3+1 D case, we know there's a SO3 level 3 transform, SON level N TQFT can control, right? But I saw that if you go one high dimension, maybe you can also do, but it seems not possible. And then you say, but we have a 3 generation of the the lepton and quarks, and if they are right-hand neutrino 3 generation, maybe we want to remove some of them, but you cannot remove 3 of them together to a TQFT. You can only remove 2 or maybe 4. 4 of them, then you can go to TQFT, and then you can add other sector. And then, for example, interesting one is that if you wanna, if you like me, also believe this Z4 symmetry is preserved, then we can add something's wrong with my pen. We can add two right-hand neutrino, and then 2 index 2 TQFT, and possibly -1 for the one natural dimensions, and then this can cancel. For example, these are one scenario. Let me see. Yeah, 2 for the TQFT, symmetric TQFT. Sorry, 2 for the right-hand neutrino, and 2 for the 4D TQFT, and 1 for the 5D invertible TQFT, and then this can cancel. So this will be again for like Fino. If you want to build a model, there's a possible many choice, but I think these are finite numbers, so it's not bad, not so bad.
But can I say that at the end of the day, you don't get to gap out all the right-handed neutrinos?
Yeah, you cannot gap out all at once the 3 of them by symmetric active. You must add you must add one extra dimension, or maybe you need to have one right neutrino left, or you need to have one for the TQFT. Mm-hmm. Just the index. These are the constraints basically of this one.
Okay. And
also should say, because Layson was here, for people who study astro and cosmology, there may be implication about this quantum criticality. I'm not expert on that, but I suppose that could mean something, but I haven't got there. Yeah.
It's interesting. Could I ask a quick question, or Chang? I don't know if there's time for me to ask a quick question.
There's always time. It's okay.
So I was going to ask about 3 generations. So are all of the anomaly cancellation that you're talking about here is taking place generation by generation? Is that right? Is there any particular indication about where 3 might be coming from?
So in my talk, all the 3 generation basically they play the same role. So they are triplicate 3 times. They carry the same index for each generation, right? But then I think you are asking why these are 3, right?
Yeah.
I don't have a direct answer in my talk, but as I say that if we want to do some model building and replace right-hand neutrino by this TQFT sector, then maybe we can have a explanation on like a neutrino mass, and in that case, actually maybe reading the data, you can possibly figure out what might be the TQFT. This is actually the technology. Actually, a lot of quantum matter and QFT people are gradually going to do this. I think it's possible, but not directly. Just based on this cancel. There's nothing special at this moment. Why 3 is
I was going to say this is probably something we could discuss later. I mean, I would be interested to discuss it later. So just to briefly say that Neil Turek and I had a paper back in October, I guess, where we pointed out that in the standard model, you could cancel the vial anomaly. In other words, the trace anomaly, the scale anomaly.
Yes.
If you add a certain number of dimension 0 conformally coupled scalar fields, but it turns out that you can cancel both terms in the vial anomaly and the vacuum energy. But it's quite non-trivial, and it only works when there's 48 vial fermions. So in other words, it only works for when you include right-handed neutrinos and when there's 3 generations. So I wonder whether it might. Yeah, I don't know. I wonder how it might connect with this whole story. But
I see. Yeah, maybe you can give a talk at Harvard. I can arrange that. I'll be happy to hear that. Actually.
Yeah, I'd be happy to. But yeah, it's anyway, or we could, yeah, and even earlier, I'd like to discuss with you about it. Maybe more like.
But in my case, I'm trying to replace right-hand neutrino to different sectors.
Yes.
But then the question is that whether those anomaly index you carry can also cancel by different TQFT or CFT sectors. I think your neutrino is more like a free fermion, right? Like quadratic or it's a fermion bilinear or coupled to Higgs. But here we are trying to cancel by like a exotic quantum phase. Yeah, and that's something certainly would be nice to understand. Yeah, if the vial anomaly can be cancelled by that. Yeah, thank you. I think there are some people also do proton triality. In that case, I think actually if you assume some baryon Z3 symmetry, I know actually there's some Z9 anomaly. In that case, I think the 3 generation might play a role. That's something I know, but I didn't discuss in my talk. I can also mention that maybe privately to you. There's some certain Z9 anomaly cancelled by 3 generation.
Okay.
Yeah.
Anyway, very interesting talk.
Well, thank you very much. Thank you. Thanks.
All right, I think.
Can I?
Yeah, please.
Whatever.
Please, thanks.
Yeah. I previously had to step out, so I missed a few minutes of your talk. Did you say that you have some argument based on quantum gravity such that the two-hooped anomaly has to be cancelled?
I have some idea, but I don't speak in my talk. Yes. These are similar to the case, like lambda 0 modes living on the boundary of a Kita chain. Naively, you may not be able to cancel the gravitational anomaly by any other way. These are the 1 + 1D of invariant and 0 modes. But I think there's also some way people try to do couple to gravitational theory, like topological gravity. So I'm just making an analogy. Yeah.
My question is, did you say that all the two-hooped anomalies have to be cancelled?
Oh, sorry. Then I'm answering a different question. In the case of asking that part is like go quickly. Is that in the case if I ask to preserve the spin time Z4, let me just show this. In the case of I ask to preserve this standard model group with spin space-time and Z4 baryon minus lepton-like symmetry, I do ask to cancel them if I assume the Z4 is discrete B minus L is gauged and preserved at high energy. And because the standard model is also gauged, I do also cancel gravitational anomaly, yes. So all these index must be 0 if I assumption
I thought you also said something about the absence of global symmetry in quantum gravity. Did you?
Yes, because the Z4, if at all energy scale, you might think B minus L type of symmetry is a global symmetry, but at high energy, if they are there, it should be gauged. So that's the statement I'm using.
Okay.
Yeah, quantum gravity for people current knowledge is that if that symmetry is preserved at high energy, it must be dynamical gauge. Otherwise, it should be broken or it's not there.
Okay.
Yeah, these are just no global symmetry in quantum gravity statement.
Okay.
Including discrete symmetry, even CPT, I think, even for non-parity, everything should be gauged. If that symmetry plays a global symmetry at some energy scale, and if it's still preserved high energy, should be all gauged.
Mm-hmm. And this requires all the anomalies you talked about to be vanishing.
Yes. Yeah. So that's why That's why I imposed that.
Okay, I see. Thank you.
Yeah, these are the most crucial assumption in this construction. But certainly you can change the rule to add in additional symmetry and do another construction. You can build another model. But as long as you try to cancel global anomaly by some ways by these new sectors, I think I will still try to call it Ultra Unification because these are beyond the Grand Unification. Yeah.
I guess the way to cancel the anomalies is not unique. So
yes.
So
but
in order to detect which way is realized in our universe, do we have to build larger and larger colliders?
Right. Actually, I do feel like so these are questions about how do we do experiments. I think we live in SM lab, so the whole thing we live here, everything is SM, but we can locally create some bubble, and possibly just inside the bubble we may create a domain wall tuned into SU5 gut. And then maybe possible. I'm just saying that it seems not possible if you think everything in a large scale, but just like a sample in the lab, it may have the ferromagnetic mostly, but it may have some doping and impurity inside, and inside the bubble domain wall, there could be a different theory. Yeah. So in the lab, it's possible.
For condensed matter systems, I think it's easier to tune the parameters. But for our universe, it may not be that easy to tune.
Yeah, it may not be that easy because in construction, I need to tune the God Higgs potential. I have no idea other than God, the creator of the universe, who can tune his God potential for us. Maybe in the time scale in the early universe, there's something you can tune, but at least in what we have, it's very hard to imagine how to tune the God Higgs potential. But since you asked this, I think I want to mention something about proton decay, because I think people are trying to find proton decay, for example, in SU5. But the reason they look for is that they believe in a SM at high energy, you might hit in a sense, go into some SU5 gut, and then you can have a proton decay through this gauge boson of this some XY boson. By the way, don't confuse with this XY boson of SU5 gut with XY global symmetry. These are different things. And if you think this conventional way, you will always go high energy to collide to look for proton decay, or maybe just see the remnant of SU5 at low energy to look for proton decay. But right now, the possibility is that suppose SU5 gut is not really at high energy, but it's a neighbor vacuum we need to tune to the other side to look for. Then we should not look for proton decay at high energy, but we should change the vacuum locally to SU5 gut, and we can easily find within that bubble the proton can decay. And that's a larger difference.
So if we can tune the parameter.
Yeah, if we can tune the parameter here, then we can find proton decay within that vacuum, but not in this one. Because possibly, depends whether we hit to go to high energy, we do have a SU5 gut. Maybe we are, for example, here in this region and go to high vacuum. Maybe there's a different constraint of the proton decay. I think these are something I think a different perspective.
Sorry for my ignorance. Is it true that proton decay only happens in the GG?
I think it's also happened possibly in other guts. Yeah. Well, it depends on the whole global structural phase diagram. I have no idea what exactly at this moment at high energy. I think today we are mostly trying to explore the zero temperature, but I'm trying to say a possibility that it may not be a problem at all. Say our SM vacuum does not have proton decay. In a sense, we may not go to high energy, go to SU5 gut, because we may not be in that parameter space. We may need to go there somewhere else, tuning God Higgs to go to the other path to look for proton decay. And if that's that possibility really holds, then we don't really need to worry proton decay. But on the other hand, I do also try to do some calculation with additional degree freedom, these new sectors. Maybe there's some constraint on proton decay, and that's something I'm also trying to carry out. I haven't find additional things. There is maybe give a higher bound to proton decay, but right now what I can do is that suppose I preserve the Z4 baryon minus lepton, it gives some channel constraint to proton decay, but I don't see significant change the ratio of proton decay. So I haven't anything significant to report. But right now I just say that there are new room to think. Just proton decay should look for in this direction, not this direction. not at high energy, but at the neighbor VAF. Yeah, and also the new modification might also give some additional modification on the proton decay rate.
Just to chime in quickly, proton decay happens in both SU5 and SO10.
Yeah. I think also
sorry, what did you say? Can you say again?
Proton decay occurs in both constrains both SU5 and SO10.
Yes.
In both cases, the usual constraint is that it constrains the gut scale in those cases to be about 10 to the 16 GeV or higher.
Yes.
I see.
I think the usual gut is already ruled out, but the SUSI gut, some of them haven't been ruled out. But I think Pati-Salam also has proton decay as well.
So that the story is non-supersymmetric grand unification is ruled out in SU5 and in SO10 if it breaks through SU5, but it's not ruled out in SO10 if it breaks through Pati-Salam. And the Pati-Salam, the sense in which but the Pati-Salam scale, the intermediate breaking scale at which Pati-Salam breaks down to the standard model can be a lot lower than this 10 to the 16 that I quoted. That's what I mean when I say that. So a theory that breaks through Pati-Salam can have proton decay, but it's just that the Pati-Salam scale is not constrained by it in the same way it is for the other two.
I see. Thanks.
Thanks for the info. Yeah, but the hope is that adding those new exotic sectors, maybe something will change. And so along the line, maybe like Justin, this local people, Justin Kopp, the researcher here, he's also working on this extend objects, global anomaly, and that's basically a new window there. Maybe they really exist in our vacuum, and it's much more, the vacuum we live in is much more entangled than what we thought in the usual SM, but there's such sectors. And it's just everywhere. I think condensed matter people know it's just here and there, because we only interact weakly through this discrete, for example, Z4, or only when we go to some higher gauge group, like the enlarged spin 10 gauge group we can communicate with. But they are just neighbor to us everywhere, except we don't really interact in a simple way. But anyway.
All right. So if no further question, that I think nicely concludes today's talk. And,
thank you.
Thanks, Juven, for this really interesting talk. It's been fun. It's been a great fun to have you.
Yeah, thank you, Tom. Yeah, it's also related to you guys' work on it's a DQC deconfound quantum criticality in 3+1 time. Yeah. Great, thank you.
Great.
Thank you, Juven.
All right.
Yeah, thank you. Bye.
Thank you,
everyone.
Thank you, everyone. Oh, by the way, Tom. Yeah.
Sorry.
I have one more email to you. Maybe you can also reply later.
Oh, okay. All right.
Yeah,
sure.
You know that.
No problem.
Yeah. Bye.
Bye.